Okay, hi everyone. Thanks for joining us for our TVS Science Colloquium today. Let me start by reminding you that this talk is being recorded and we will later upload it to the TVS YouTube channel. After the presentation by our speaker, there will be plenty of time for your questions, so please save them until the end of the talk or type them in the chat. And now I would like to give a warm welcome to our speaker today, Ryan Ridden, who is a postdoctoral research fellow at the University of Canterbury Research School of Physical and Chemical Sciences and is working with Michelle Bannister. Ryan received his PhD from the Australian National University in 2019, following which he was a postdoc at the Space Telescope Science Institute at Johns Hopkins University. With expertise in transient astronomy, photometric pipelines, and instrument calibration, he's leading a program to search for rapid extragalactic transients with the Kepler and TESS space telescopes, and is working on automating the Ōtehīwai Mount John Observatory. Today, Ryan will talk about the joint coast survey with the Ōtehīwai and Rubin observatories. And please, Ryan, the floor is yours.
Thank you very much. Kia ora koutou, everyone. Thank you for coming along today. I'm going to be talking a little bit about what we're hoping to do in the future and what we're planning to do this summer and get everyone's input on a potential co-survey that we want to run between the Rubin and Ōtehīwai observatories. So before we get into what the observatories have, I thought it'd be good to go through some context and the global picture of things. So here we have the world, or at least the important part of it for this talk. And you will, of course, all be familiar with where the Rubin Observatory will be placed, nicely in Chile. And quite often it's the main next observatory people think about are the ones in Hawaii that will pick up after the Rubin Observatory. But the telescopes in Hawaii have a fairly northern-centric viewpoint. So their declination limit, say for pan-stars, sits just above New Zealand even. So it doesn't reach all the way south and cover all of the potential things that the Rubin Observatory might find in a nightly basis. So this is where the strength of Ōtehīwai Observatory can come in, because we are a very far south observatory located in the middle of the South Island of New Zealand. And we're kind of the next southern observatory over from the Rubin Observatory. So we can pick up all of the things in the south that Rubin might have discovered the night before. And it's about a 7-hour time difference between when something is at its peak in the Rubin Observatory to when it will be at Ōtehīwai Observatory. So there's a nice time lag between the two observatories. But more directly, in New Zealand, Ōtehīwai Mount John Observatory is located right around there. So it's in the middle of the Southern Alps, and it's protected by them from cloud for the most part. So we have pretty good clear night ratio. So about 60% of the nights are clear and 20% have partial cloud. And then the remainder have cloud, so you can't really do much with them. But overall, it's a very good site for observing. And at the observatory, we have a lot of different things, and it's a stunning location. So if you ever get the chance to come to New Zealand and see Ōtehīwai Observatory, you'll be most treated to wondrous sights. So we have Te Tere Oti Moana, or the Southern Alps, in the background there. Then we have two lakes either side of Ōtehīwai, the Takapo Lake, which is a lovely big glacial lake, and Takamana, which is another little finger lake sitting next to Ōtehīwai. But on top of the mountain itself, there are a number of different telescopes. And the first one we'll look at is the 40-centimeter Dark Sky Project telescope. And Dark Sky Project is something a little bit different. It's a really cool program that's being run by Ngāi Tahu, which is the local Māori iwi of Canterbury. And they're building an astrotourism program there, as well as an outreach and education program. And we'll actually be working closely with them from the University of Canterbury to build teaching and educational resources, which are being supported by the LSST Kickstarter grant. So very thankful for that. And there'll be some really cool things that will be coming out of that Kickstarter grant as we work closely together with Dark Sky Project. But other things that we have on the mountain are two 60-centimeter telescopes. So one Bowler and Chivens telescope and the other Optical Craftsman telescope. So those are the next two biggest. Then we have the 1 meter McClellan telescope, and then the largest telescope on the mountain, the 1.8 meter telescope. So the 60 centimeter telescopes just have images on them at the moment, and the 1 meter McClellan telescope has either an imager on it with a range of different filters, or the Hercules high resolution Echelle spectrograph, which has varying levels of R values and has a wavelength range of 380 to 880 nanometers. But the biggest telescope we have on the mountain is the 1.8 meter telescope, which has primarily in the past been used for the MOA survey to spot microlensing events. And this telescope has a few things. It's, as you might expect, has a primary mirror diameter of 1.8 meters, and the declination limit for the 1.8 meter, along with all of the other telescopes on the mountain, is about +10. So we're a little bit short of Hawaii, for example. And the time available that we have at the moment is around from October to February, so the Southern Hemisphere's summer. So that's all time that we're working out how to deal with, and will be time that would be very interested into putting into a co-survey with the Rubin Observatory. And on this telescope, there is the MOA-CAM 3, which has a selection of kind of strange filters because it was built for microlensing science. So you have the kind of standard V band and I band, but then there's also this wide MOA R band, which is kind of a combination of R plus I. And this imager is pretty large. So here's a single snapshot of the Orion Nebula. So it's a 1.65 by 1.32 degree field of view. And in about 300 seconds or 5 minutes, you can get to 21st to maybe 22nd magnitude on a very good night. And overall, if you're looking at the full width half maximum of objects on this detector, of which we have 10 CCDs that make up the array, you end up with something like this, where the average full width half maximum is around 2.3 over the course of the entire year. So this is, as you would see it on the detector. It's not necessarily the sightseeing, because there are various focusing quirks to do with the telescope itself that will make this a little bit different from the sightseeing. So all of these telescopes have been included in New Zealand's in-kind contribution to LSST, or the bid for that. And it comes in two parts. So we have the archival data from the 17-year MOA microlensing survey, which is being delivered by the University of Auckland. And then there's access to Ōtehīwai Observatory and interacting with the telescopes there through the AON framework. So the plan is that all of these telescopes will be remotely accessible and robotic, and they'll be interacting with the AON framework. So investigators from the Rubin Observatory will be able to submit targets, which will then be followed up. As I said, we're kind of a 7-hour time lag behind Rubin Observatory, so we can pick up the things that were potentially just detected by Rubin that night. So with all of the telescopes that we have at Ōtehīwai, when we're discussing the in-kind contribution, an idea came up that perhaps we could do a co-survey between the Rubin Observatory and the Ōtehīwai Observatory, since they're both Southern Hemisphere and they're uniquely placed in longitude and latitude. So as I mentioned before, this is kind of where, as far north as we can see with Ōtehīwai. So we started thinking about building this co-survey program, which we're planning to test this summer, thanks to the generous support of the LSST Kickstarter grants. So the main points of this co-survey are that we can do coordinated follow-up of LSST targets and fields, whatever might prove to be interesting. We're about 7 hours behind, so nighttime for us is a little bit later, and vetting things we could do, things like vetting low redshift contaminants, and potentially many other things. So we're just in the planning stages at the moment, and we'll be testing all of the different ways of going about the co-survey this summer. So at the end of this talk, it'd be great to have everyone's input as to what might be the most useful way to spend our time to test synergies with the Rubin Observatory. So an example of an existing co-survey type thing that we're building at the moment is working with the DART program, the Double Asteroid Redirect test. So in this test, sometime next year, hopefully, the spacecraft is going to hit a little moonlet of this asteroid here and change its orbit a little bit, which will then change parameters and its brightness. So we'll be coordinating our observations from Ōtehīwai with the 1.8 meter with SOAR, which is on the same mountain range as the Rubin Observatory. So it'll be a nice little test between the two systems. So far, we've been looking at different things to see what we could do with the co-survey. And the most obvious thing would be to look at the deep drilling fields so that you would have a slightly longer coverage on those. And as I mentioned before, things that the 1.8 meter can pick out will be probably much closer than the things that Rubin will be able to see. So you'll be able to vet the low redshift candidates or things like stellar flares or something within our galaxy, and you'll be left with a cleaner extragalactic sample. So a lot of the deep drilling fields are quite north. This one is the best one for us during the southern summer, the extended Chandra deep field south. So that's up for most of the summer for us and quite high in the sky. So it's a really good target. And we've been working out already how we can best tile this field to get the best observations of it. And this is kind of the configuration that we're going with at the moment, where for one LSST pointing, we'd need about 6 pointings from the 1.8 meter with MOACAM 3 to cover the entire field of view with a little bit of overlap. So at the moment, we've been testing this with 5-minute exposures. So between all of these, it takes about half an hour to tile a field in a single filter. So if we were to do multiple filters, say R and V band, then it would take about an hour for one complete pass. And while doing these tests, we've encountered something that will be in all of our future, unfortunately, and something that will impact Rubin significantly, as has already been worked on, is mega constellations and satellites. So these are just some frames from the tests that we've been doing. And you can see there are nice, well, not nice, quite horrible bright satellite streaks running through the image. So we have, within all of our images, we have all of these satellite streaks in them, which may be useful to members of LSST to see, or to either test their data reduction pipelines to see how we can detect and potentially remove these asteroid streaks. Satellite streaks. But it may also prove to be interesting to have a kind of real-time analysis of what the southern deep drilling fields, at least, what kind of contamination they'll have from mega constellations. So we can monitor these fields and see how they evolve over time, and perhaps give Rubin a better understanding of what the scenario will be like once it comes online in a few years' time. So as well as these kind of scientific impacts, in New Zealand, we're taking particular interest in these mega constellations because they'll have a profound cultural impact as well. Over recent years, there's been a resurgence of appreciation for local Māori customs and traditions, one of them being the celebration of Matariki in around June and July. So as Matariki rises at that time of the year, it's known as celebration, and kind of a new year starts at that point. So the question for us becomes, well, what will the mega constellations contribute to this? And what will it mean to have satellites streaking across Matariki? So New Zealand is very engaged in this problem, and we have a space agency which is actively pursuing this and trying to understand how the field is going to change, and what kind of impact it will have on the country. So these are the different things that we have at Ōtehīwai Observatory and different aspects we've been thinking of. So just kind of a brief introduction to all of that. But the thing that is most interesting to me and Michelle are knowing what it is that all of you would want us to do. So what would your dream co-survey be like? So what kind of filters you'd want, what kind of cadence you'd want? Is it necessary for a full, for a 5-minute integration time, or would a shallower depth and a larger area be more useful? And as well as deep drilling fields, are there any other parts of LSST's footprint that we should be considering, or targets that we should be testing to see what kind of photometry we can get on them? And as well, the best way to get data to everyone who might be interested in it. So if possible, I'd like to just kind of open up now to everyone. And if you have any thoughts on what you might want in a co-survey, knowing now the instruments we have at Ōtehīwai.
Okay, thank you, Ryan. So yeah, please, the audience, if anyone has any suggestions, questions, and so on, yeah, you can just raise your hand. And Paula, you can go ahead.
Hi, it's great to see New Zealand being an active part in LSST. It's really nice to see that happen, and I was lucky to be able to observe from Mount John when I was part of my sabbatical years ago. We were doing colorimetry. But in answer to your question, I think the filters would be an important thing. Your filters are, I don't know if you how much funding you have to get new filters. Are you planning to get filters that either match the LST data set, or preferably spend more time in the blue, because LST is not going to have as much coverage in blue. So I think in terms of filters, either that set or a blue, and spend more time in the blue would be great. The cadence, again, you know, if you have a blue filter and can pick up some of the short variability, that's one of the things that LSST is not going to be great at. That would be a huge help. And I think having a larger, from my standpoint, I work on cataclysmic variables, having a larger area coverage at maybe a shallower depth would be optimum for the kinds that my field would. And are you planning to spend more time on Magellanic Clouds, for example? Because that's one of the, I don't think it's exactly in the deep drilling fields, but it's one of the areas that I think the whole team is thinking about spending more time on. And that would be a good thing to be on as well.
Yeah, we certainly can spend more time on the Magellanic Clouds. So thanks for your input there, Paula. The Magellanic Clouds are generally what the 1.8 meter looks at anyway with the microlensing program. So it's very, very well set up to tile the Magellanic Clouds. So we have those, that is a possibility. As for filters, at the moment, we're working with what we've got, but certainly we'll keep in mind blue and another filter set for the future wish list that we might be working on. Michelle might have something to add to that.
Kia ora, folks. In terms of filter purchasing, we have been looking at this, but it is going to be a little bit tricky because the MOACAM 3 is not terribly blue sensitive. So there's not a huge amount of, we're not going to get UV sensitivity out of it, near UV sensitivity out of the current MOACAM 3. So for the kind of 5-year plus timeframe, it is something we're exploring of what additional instrumentation, particularly in photometry, we could add for the observatory as a whole. So yeah, I would definitely be interested in, say, for instance, looking at a simultaneous multicolor camera that we could look at for a few years from now. But this is the instrument we've got at the moment. So mostly just seeing what we can do with what we have and then look ahead to what we can purchase in the future.
Okay, thank you. Rachel?
Hi, everybody. And thanks very much for this talk, Ryan. This is a fantastic resource, and I'm super excited to see it being available for TVS and Rubin as a whole. Obviously, I'm particularly interested in galactic plane survey, but Paula has kind of highlighted some of what I was going to suggest already. So in the interest of channeling some of the other science that TVS does, I wondered if you had considered doing making use of the wide field of this facility to do follow-up of things like gravitational wave alerts and target of opportunities in coordination with Rubin, which now appears to be going to do target of opportunity follow-up.
Yeah, that's a very good point. And thank you. I think with the discussions, Rachel, that led to this idea of a co-survey in the first place. It was very, very cool and very exciting for all of us, I think. Yeah, so following up of things like gravitational waves is definitely something that we'd be interested in doing. At the moment, the University of Canterbury has complete access to the southern months, but we're still have opportunities to do interruptions to the standard MOL program throughout the winter months. And I'm sure they would be keen as well to track down some cool events like kilonova. They do have a fairly long running GRB follow-up program as well. So they have experience in rapid follow-up for such events. So yeah, it's definitely something we'll be interested in. There may be a way for us to devise a test to see what kind of the most effective way it is for, given some random search area on the sky, how we could best tile it with the 1.8 meter. That's actually a very good idea. So maybe I'll look into that. It could be fun to see if we can code up something to best predict a search path.
I think there's a lot of effort going in with some other resources out there. To draw attention to the projects such as Treasure Map, which is designed for lots of observatories to say where they're going to be observing either have observed or will observe in the near future, to help coordinate that kind of thing. So integrating your observatory with that general effort is, I think, really, really valuable.
Yeah, that's a very good point. I'll definitely look into that. Thank you, Rachel.
Thanks.
Okay, there's some input or maybe a question from Shri.
Yeah, I actually have two comments. More in the way of question. It's by no means obvious to me at all, actually, that co-observing is valuable. Of course, observing is valuable in the sense you observe, you get data. So let's not be at that level. Is it supremely valuable? Is it strategic? It's not obvious to me. Okay, I didn't find you articulate a clear purpose there, and maybe I missed that, or maybe it's known to, it's obvious, but I would like to really understand in a sharp way, what exactly are you trying to get out of that?
Yeah, that's a very good point. Sorry, I should have covered this in greater detail in the talk. So the obvious areas for me, at least, that the co-survey would provide the greatest input are for, say, for transients. So LSST will discover lots of transients, either galactic or extragalactic. And some of them may be discovered quite early on in their phase, so just when they're rising. So an extra data point just a few hours after discovery can be very important for nailing down the rise of these events and understanding then the process that led to their detonation and subsequent formation. Another point that could be very useful for solar system-based science is LSST will discover many, many asteroids and other things within the solar system. And just from discovery, you have one or a couple of data points which you could create an ephemeris for to predict the path of the object, but it won't have a very well-constrained ephemeris. So then if you were to use a wide field imager like the 1.8 meter to more or less immediately image the region that you expect it to be based off the LSST ephemeris, then you get a much better idea of or much better constraints on the orbital properties of this potential asteroid or other solar system object. So those are the two immediate things that jump to my mind when thinking about how a co-survey could benefit the Rubin Observatory, as well as you'll be dealing with, for transients, there'll be enormous volumes of data, enormous amounts of candidates that will be coming out of it. So it will be helpful because you can't take spectra of everything to see what redshift they might be at. You can use the Ōtehīwai Observatory and its facilities to then see, well, if the 1.8 meter can see it, then you have an idea of the distance it is. So you can rule it out of your, say, high redshift supernova sample or something like that. And then the one final point with the mega constellations is we can provide information now of how the, say, deep drilling fields or Magellanic clouds will be actively being impacted by the more and more satellites going up into orbit. So I think there are lots of ways that even a smaller facility like Ōtehīwai can provide valuable information to the Rubin Observatory based off of its location and its smaller telescopes, but they also have an important role to play in filtering the data and understanding it.
Well, I would say I have some experience in this field, and I don't find your points convincing. And let me answer in that order. So let's say that your goal is to find young transients. The point is that LSST will go to 24th magnitude right away in a 30-second exposure. So you're then going to be looking at transients that have to rise from 24th magnitude to 21st in the 7-hour time difference. That's an incredibly short rise time. Okay, the number of such objects will be very limited. It really would be, I would say it's essential if you want to go this way to actually do the computation of the rates. Okay, so this idea of looking for young transients, you really need some match. You won't need a good match in magnitude if the areas are very large, but it's the opposite way. The area is the opposite. That is the field of view of LSST is bigger than your field. So it should be the other way around if you want to do any co-observing for that specific purpose. For the asteroids, LSST will find a lot of asteroids, but the main strength of LSST finding asteroids is the faint ones. For the ones at 19th mag, they're much better experiments which cover the sky in the most optimal way for asteroids called ATLAS. And ATLAS will soon be installing, I believe, something in South Africa and maybe, I don't know where it's Chile or Australia, someplace there. They have 2 stations in the south. So at that level of 19th to 20th, LSST has nothing special for asteroid work at all, because these are dedicated facilities. And you could do that ephemeris thing much more readily for those systems than the faint asteroids that LSST will find, which will dominate the asteroid, dominate the asteroid points. So my main thing would be a slightly different one is, if I was asking myself the question, if I was a young person all over again and I was in New Zealand, what is a unique science I would do? Okay, and if I had a 1.8 meter telescope, I would say the unique science would be something which has to do more with follow-up. And there are plenty of surveys that are happening at the magnitude level that your facility can operate. Your photometric limit is 21-ish. So that means you can do nice light curves at 20th. You could do low resolution spectroscopy, but you don't have that instrument. And getting this sort of, what should I say, the additional data, do the filtering, been there, done that, I don't think it's that useful. Okay, in fact, that was the very concept of PTO phase 1, was to use the 48-inch telescope to generate the discoveries, and the 60-inch, which is the right way you want to do in this business. You want to actually do the follow-up with larger telescopes to do the contextual data, which is colors and so on. So I really think that if you want to do some sort of a stunning, unique science, sort of done in New Zealand, it may not involve LSST, or it may involve LSST in a more minor way. That is, LSST would have found very nice, interesting binaries, with exquisite light curves. In fact, that's one thing LSST will be terrific at, actually. It'll make some of the best light curves ever. It's a really photometric engine, non-parallel. And then you could choose and follow it up, in which case I would really switch to an EMCCD or a CMOS detector. Anyway, sorry for this long analysis, but that's what I would do if I was a young person wanting to make my own name in New Zealand in the year 2021.
Thank you. Thank you for your input there. It's definitely something we'll take into consideration. I still think, I think I disagree with you though. I think it is very useful to have these facilities and to have this follow-up capability. And one key example I would give would be the young supernova experiment, where they're showing that with staggered observatories, you can actually do some pretty cool science and get supernova in the very early stages, or just transients in general. And I think, Michelle, if you have anything
Ryan, but I know the YSC. The YSC matches PS1 to ZTF.
Yeah.
Yeah, it's not matching full magnitude difference. That's the point. There has to be a magnitude match here.
Yeah, but it's still a staggered observation. So it's, we may only be able to pick it up, say, a day or two after LSST first discovers it, but that's fine. We still get data points early in the rise to cover that and get a better coverage of how the event actually rises. So there is still scientific value in taking these observations.
A young supernova is now being discovered with only a few hours since its explosion, almost every night now. A supernova which is a day old, few years from now, is not valuable.
Oh, yeah, we'll take that as your opinion on that matter. And Michelle, if you want to say anything about the solar system science.
Yeah, so I'm in solar system science collaboration, so I guess I could speak to that point. I would note that on the question of NEO follow-up, yeah, absolutely, Rubin is going to go a couple magnitudes deeper. But what we have been seeing in coverage across the NEO follow-up side of things is that longitude-wise, there has been a persistent gap in Southern Hemisphere coverage that is well established for the last, couple of decades almost. And and we have a program running on the 1 meter where people have been providing astrometry into NEO follow-up at the magnitudes that facility can reach. So being able to extend that to the 1.8 meter, I think we're still going to see a niche of coverage of NEO follow-up that simply isn't being met by, there's a lot of ocean. There's no telescopes in it except for us. So I think it's going to be a relatively small niche, but it's still useful for the planetary defense case as well. And I would say, also, absolutely, Atlas is expanding into the Southern Hemisphere, which is great, but they're on the other 2/3 of the planet. So, we are, of course, talking to Atlas about this as well.
Okay, thank you. Are there any further comments or inputs that someone would like to share? Okay, as I'm coming from a slower blue transient field, I have to definitely agree with Paula that one thing that would be very useful is observations in bluer bands. And I think this is also very important to discern between different types, either it's a supernovae and which type of a supernova, or maybe a tidal disruption event, AGN, and so on. I do have a question about, you mentioned that you have a spectrograph on one of the telescopes, and I'm just wondering if that can be also included in this survey as spectroscopic follow-up for like some interesting transients that are happening.
Yeah, for sure. The challenge there is that it has a pretty bright limiting magnitude. but it is definitely something. If there is a valuable target to look at, would be certainly keen to do that. And I think there's a low resolution spectrograph that's maybe getting put on a telescope sometime soon that might also be useful for that purpose. So yeah, we'll definitely keep an eye on how we can also integrate the 1 meter and the spectrograph capabilities, or spectroscopic capabilities, with the other aspects of the survey.
Okay, thank you. Yeah, that would be great, I think, because yeah, we'll really have limited spectroscopic follow-up, I think. Yeah. Okay, do we have any other questions or any comments anyone would like to share?
This is Shrey again. I'd like to add that LS4 should be on next year. And that would, in fact, be a fantastic complement for you to work with.
What was it, LS4?
Yeah.
Okay.
That'll be Chile, and it will go deeper than Atlas. So for it'll have a 20 square degree field of view. It's actually very good. Excellent pixel optimization for LaCie. And the point I was making was not that the small telescopes don't, in fact, I've built my career using small telescopes, is when using small telescopes, there has to be a magnitude match. And to me, something like Black Gem, LS4, and Atlas represent a great complement to your telescope than LSST. That's mainly because it's the other way around. So smaller telescope with larger fields of view can do something interesting with a larger telescope and a smaller field of view, but not the opposite way.
Right. Yeah, we definitely take these points into consideration, but yeah, we will be working on this co-survey with LSSD, and it will be a matter of trying to find the best way to use the facility that we have here to complement the Rubin Observatory. And that's something we will undertake. There will be challenges, and perhaps it might not be as effective as we would hope, but still there will be useful data to come from it. And I'm sure we can optimize it to give the best results possible. But we will also explore these other possibilities of integrating with these other surveys you mentioned. So thank you for those points.
I'd also note there is an element of how the international community comes together on this, right? LS4 has not reached out to us and gone, hey, it would be lovely if we had international collaboration across the Southern Hemisphere. Rubin Observatory has been super welcoming and really keen to help bring a relatively small astronomical community in our country into part of this big international effort. So yeah, it makes a difference.
There is another comment or question from Paula.
Yeah, I just have a question about what do you anticipate in terms of how soon the data that you take would be available? I mean, is it going to be immediately that same night after will be just put into the archive and available, or because that will matter? I mean, it will help if it's, the sooner the better.
Yeah, that's a very good point. So we're planning on more or less real-time reductions as fast as we can do them. So we're getting a dedicated Ōtehīwai server installed to handle all of the reductions. So that should be nice and fine-tuned sometime during the next year. The question of where is the best place to host the data so that external collaborators can get access to it is something that we'll need to think about. It may be that Noir Labs could be the best place to host that, or some other avenue. So we'll definitely try and make things available as soon as possible, within like a day or less is the goal.
So yeah, I don't know, Rachel, if you have an idea of some, I mean, you're not going to be the only ones that are contributing. There'll be other small telescopes that are all going to be, maybe doing some co-observing at some point. And I don't know exactly how that data is going to be accessible to the whole world, basically. I don't know, Rachel, do you want to, what is the plan for that?
The plan is really on each individual facility, certainly in the in-kind program. It's on the individual telescope facility to serve the data in a timely way. And most of them are working, they either have their own archive for serving information, their data already, or they're working with the Nuara Lab to share the data through the data lab. But yes, and making it available in a timely fashion was one of the criteria in which the in-kind process was recommending that surveys make the data available as fast as possible.
Yeah, it seems like we're going to need some kind of coordinated effort to make it most useful in the end.
And several levels, I think, yes.
Okay, are there any questions that are still on your mind, maybe, or any comments? Okay, doesn't look like that. So I would like to thank again Ryan for your very nice talk, and also Michelle for your comments and input, and also everyone else who shared their input today. And with this, we can conclude today's colloquium, and I'll see you next month. Bye.
Thanks, Ryan.